Before solving partial differential equations, we need to take a step back and consider, in this case, first order ordinary differential equations here. In general, when we do have the partial differential equation, the function will depend on two variables. For example, the option will depend on time and the asset value. But in this case, in the ordinary differential equation, we're going to consider the equations where the function here will depend, for example, the function we're going to call it y will depend on just one variable, one independent variable. In this case, we're going to call it t, but it could be x or any other name for the independent variable. So in this case, actually, before going to the numerical methods to solve these first order ordinary differential equations, we're going to consider, even though we are going to do the very simple way, a kind of analytical methods that could be considered, very simple analytical methods in order to have the analytical solutions. So first, let's settle which is the first order ordinary differential equations. As we have said, we do have a function which is going to depend on t, and let's consider that this function we know, and that's the equation, the ordinary differential equation is saying to us that this equation, this function, satisfies this equation here. As you can see here, we have that the derivative of y with respect to time is this function. This function depends either both on time and on y, and could be any function actually. And besides that, as in order to have the solution for this function, because actually solving that equation, we need to have that the function that satisfies this equation here. And in order to do that, finally, we will need to do an integration here. And in order to have the precise function that satisfies this equation, besides the equation, besides the differential equation, we do need an initial condition. An initial condition has to be settled, specified as well. In this case, we do have that the y function at some initial time, we're going to call it time t naught, it's equal to y naught. Okay, this is therefore this is actually the first order differential equation that we do need to solve. And in general, this is actually very difficult for any function f. That's very difficult to have analytical solution. And actually, in general, they do not have analytical solutions. That's why we have to rely on numerical methods in generally. But for some specific case, for some simple case, we can do something. We can get some analytical solutions. And in this case, we are going to consider a very simple case just to see how we can get the analytical solution for a particular simple first order ordinary differential equation. And the simple case we're going to consider is the following. Let's consider that in this case we do have that the function here depends on two functions here where the time and y dependence is separated. So that let's consider this case where this function can be written the following way: some function g which depends on time times some function h which just depends on y. So in such a case, yes, we can have analytical solution for this ordinary differential equation. How can we do that? Okay, let's consider the equation in this case. This is the equation we do have again, where the two time and y dependence of this f function here are separated. Besides that, we do have this is the initial conditions where the y function is satisfied, In this case, this method is called the variable separation method that can be done actually whenever you have such dependence here, whenever a time and y dependence are separated. And the strategy that we're going to follow is the following. Here what we're going to do is we are going to bring the time, sorry, we're going to bring the y dependence to the other side here. And on the other hand, we are going to take this differential t here to the right. Therefore, everything on the left will depend on just on y, and everything on the right is going to depend on t. So here we have, as if you bring this h function to the left, we have that h function which just depends on y times differential y, it's equal the g function which just depends on t times differential t, because we're bringing differential t to the right. And once we have here, now we can do the integration. And we do the integration. When doing the integration, we're going to put some here the limits of the integration in order to implement the initial condition that the y function is satisfying. So it basically means that we are going to consider the integration for some initial time t0, where the function y is taking the value y naught as it's specified here in the initial condition to any time t where the function is going to have a value y, because actually we do want to have the value of the function y for any time t. And when doing that integration, if we separate and from here, from the function we're going to, from the expression we're going to have here, if we're able to take and separate the y in terms of the of time, that's going to be the solution for the y function that satisfies this ordinary differential equation and that initial condition.